Hi everyone, this is Miss Ward. Tonight your notes are going to be on Motions in Two Dimensions unit, Concept 2. It's going to be talking about relative motion. Now, when I made your notes, I intentionally separated this section out because I wanted to make sure you guys understood it, and it kind of stands alone. However, looking back on these slides, I realized that this was kind of silly to make its own concept because there are literally 2 slides that go along with this. So these are a very short set of notes. So just wanted to kind of give you the heads up on that this is not going to be particularly long. Okay, so this concept is really honestly pretty simple, but like I said, it kind of stands alone from the other ideas and things, which is why I separated it into its own little concept. So when we're talking about vectors, we're describing the relative motion. So what that means is it's the motion of one object relative to another object. So relative means as like when we compare. So the motion of one object as compared to another object. For example, if someone is walking 1.2 meters per second on a train going 7.0 meters per second, then their motion relative to the ground is 8.2 meters per second because the ground is still and the train's already going 7 meters per second, and then you're adding an additional 1.2 meters per second on top of that. So if we compare you to the ground, you're going 8.2 meters per second. If we compared you to the train, you were only going 1.2 meters per second. So that's why it's important. If that same person was walking to the back of the train with the same velocity, then their relative motion to the ground would be 5.8 meters per second, because instead of adding their motion to that of the train, they would be going against the motion of the train, and therefore going only 5.8 meters per second compared to the ground. If we were comparing their motion just to them, if they weren't on a moving train, if they were just on still ground, they would be going a negative 1.2 meters per second because they're going in the opposite direction. So it's really all about perspective. So many problems in physics have to do with the perspective that we choose to look at them with. And with vectors, just like anything else, we define our parameters in the problem. So each problem will be different, and it's important to read through and interpret what you're comparing your motion to. Okay, let's look at a quick example. A worker of a train climbs a ladder with the speed of 0.20 meters per second in the y direction as the train coasts forward at velocity equaling 0.7 meters per second in the x direction. Find the speed and the direction of the worker relative to the ground. Now, our last concept, we worked on our functions of a triangle when dealing with distance. This time we're going to be looking at velocity, but the same rules apply. We can look at any of our functions, whether it's velocity, motion, acceleration. We can use our right triangle trigonometry to solve any of them. Again, it just depends on the parameters of a problem. Also, if you hear singing in the background, I apologize. My brother-in-law just went to go take a shower, and I can hear him singing from the other room, so you probably can too. Okay, so let's draw what this motion might look like. So they told us that we're climbing up a ladder with a velocity of 0.2 meters per second, and the train is traveling forward with a velocity of 0.7 meters per second. And we want to know what our overall motion is, which is right here. So what we're solving for is our vector, which is this part of their triangle here. It is our hypotenuse. And when they say they want to know the direction that we're traveling, what that means is they want to know the angle relative to the ground. So we need to find both the angle as well as the vector. So we have our trig functions, sine, cosine, and tangent, and we have our equation a squared plus b squared equals c squared. We'll have to use both of those things in order to solve this problem. We will be using our a squared plus b squared equals c squared to solve for the length of our vector, which is our overall velocity, and then we'll use tangent function to solve for the angle above the horizon. So solving for the length of that vector first, a squared plus b squared equals c squared. C squared is always the hypotenuse. A and b, doesn't matter which side you plug in where. So we've got 0.2 squared plus 0.7 squared equals c squared. So you get 0.04 plus 0.49 equals c squared. So 0.53 equals c squared. Remember to take the square root. And you should get 0.73. And this is meters per second because, again, we're talking about velocities. So our overall velocity that we're traveling is a 0.73 meters per second. And that should make sense because it should be more than either of our sides. Okay, so now let's look at how we solve for that angle. In this case, we're going to use our tangent function. So tangent of theta equals opposite over adjacent. And we just plug in our pieces. So tangent of theta equals opposite. Remember, opposite is the side that's not needed to make the angle. So if we look at our angle here, it opens up to the y side. So our opposite is going to be the y, which is 0.2. And then the adjacent is the side that makes the angle. So that's 0.7. So tangent of theta equals 0.2 over 0.7. Now, just to remind you, if you need to solve for theta, and what you do is you take the inverse tangent. So theta equals the inverse tangent of 0.2 over 0.7. Now, inverse tangent is found by hitting your second button and then the tangent button on your calculator. So that's that tangent to the -1. It's the inverse tangent. So hit the second tangent button and then 0.2 divided by 0.7, and you should end up getting theta equals 15.9, which we would then round to 16 degrees looking at our significant figures. Because the numbers they gave us originally to start off with were technically 0.20 and 0.70, so there should be 2 sig figs in our answer. The same thing applies to our answer back here, which is why we rounded to 0.73, 2 sig figs, again in this answer as well. Remember, when we look at our sig figs, you're looking at the measurements. So in this case, the 0.20 and the 0.70, you do not worry. If they had given us an angle, you wouldn't worry about the angle. You don't worry about your angle when you're counting your sig figs. Okay, that's it for tonight. Make sure you do your whisk. If you have any questions, make sure you include them on there, and we will talk about this in class together on Monday and do some example problems. Have a great night.